one technique that we learned how to complete in the laboratory last year was gravimetric analysis. So in gravimetric analysis, what happens is you allow a reaction to occur, a precipitate is formed, and then you're actually able to collect that precipitate, wash away the spectator ions, and measure the mass of that precipitate in order to then determine, hey, what is the mass of the precipitate that formed? Okay. What if you don't produce a solid though? What if you produce a gas? Well, gases, just what you would observe is you would just observe bubbles. But what we can actually do, and what we're going to be doing in this laboratory technique, is actually collecting the gas. If we collect the gas, we can measure the volume of the gas, and using the ideal gas law, we can then determine the number of moles and potentially the number of grams of the gas that we produce. So this technique is called collecting a gas over water. So when a gas is produced, if we're able to collect it, which we're going to be able to in this lab, if we use the ideal gas law and Dalton's law of partial pressures, which I'll explain in a second why we need to use that, we can actually determine the number of moles or the mass of the gas that's produced. So let me explain this process of collecting a gas over water with an example. So here you have potassium chlorate. It is reacting, it's decomposing once it's exposed to heat into potassium chloride and oxygen. So that potassium chloride stays a solid and the oxygen is actually going to be released. And so in this example, the way that they collect the oxygen gas is they allow it to travel through that tube. It looks kind of like a straw, and then it's collected in that beaker there. Now, that beaker was initially completely filled with water. And so as the oxygen bubbles into that beaker, it forces the water out. And so as the water level moves down, that represents the volume of gas that is now filling that beaker. All right? So why do we care about volume? We're wanting to figure out the number of moles or the mass of the gas. Well, if you know the volume of gas that's released or produced, if you know the pressure, and you know the temperature at which this is happening, you can use your ideal gas law in order to determine the number of moles or the number of grams of your gas that are produced. There's only one complicating factor, and that's where Dalton's law of partial pressure comes in. Okay? The total pressure within this beaker is going to be equal to the atmospheric pressure. Our temptation is to say, okay, the total pressure in there is going to be the pressure of oxygen, but it's not. The total pressure is not only going to be the partial pressure of oxygen, but it's also going to be the partial pressure of water. Since you are collecting a gas over water, the liquid water is going to be constantly producing gaseous water at the same time. So the water vapor itself will exert a pressure. So the total pressure is going to be not only the partial pressure of oxygen, which we would expect, but also the partial pressure of water. So that's where Dalton's law of partial pressure comes in. We say that the atmospheric pressure is going to be equal to the total pressure, which is the partial pressure of oxygen and the partial pressure of water. Which might beg the question, well, how do we figure out the partial pressure of water? What do we do? I'll explain it, don't worry. But ultimately, you will know in the lab the atmospheric pressure and the partial pressure of water. And with that information, you can then determine the pressure of oxygen. With the pressure of oxygen, the volume of oxygen, the temperature of the oxygen, you can then determine the number of moles by using the ideal gas law. So let's look at an example. So here it says if oxygen gas is collected over water at 30 degrees Celsius and the atmospheric pressure is 101.246 kilopascals, what is the pressure of dry oxygen gas? So that is my first step here, okay? So remember, my atmospheric pressure equals the partial pressure of oxygen plus the partial pressure of water. My atmospheric pressure is 101.246. I'm looking for my partial pressure of oxygen. What is my partial pressure of water? Well, I know that this is happening at 30 degrees Celsius. So I look online, or I look at this table and I say, okay, at 30 degrees Celsius, the vapor pressure of water is going to be 4.246. All right, so my partial pressure of oxygen, to answer this question, is 97.00 kilopascals. Thank you, Dalton's law of partial pressure. What about the ideal gas law? So again, I know I'm at 30 degrees Celsius, and I discover that I've collected now 30 mils of oxygen gas, right, by actually measuring it on the tool that I decide to use. So I know my volume, I know my pressure, I know my temperature. I can use my ideal gas law, but I have to be careful. Keep in mind that your pressure needs to be in atmospheres, volume in liters, temperature in Kelvin. So I've got to convert. So the first conversion, I have 97.000 kilopascals. I'm going to divide that by 101.3 because remember there are 101.3 kilopascals in an atmosphere, and I get a pressure of 0.9576 atmospheres. For volume, I have 30 mils, so I'm going to divide that by 1,000 to get into liters. And then finally, for temperature, I have 30 degrees Celsius. That would be 303 Kelvin. Okay? So I'm going to plug in all of my numbers that I have into my ideal gas law, and then I can solve for my number of moles, which is 0.00115 moles. Okay? So we're going to actually be doing this process in the lab. Just keep in mind that this is another way of actually determining how much of a product is produced. Gravimetric analysis only works if you have a solid. So if you're producing a gas, you want to collect your gas over water and use this technique. So let's look at one more example.
Okay, when magnesium reacts with hydrochloric acid, a volume of 0.355 liters of hydrogen gas is collected over water at 26 degrees Celsius. The vapor pressure of water at 26 degrees Celsius is 25 millimeters of mercury. If the total pressure is 7.52 millimeters of mercury, how many moles of hydrogen were collected? Okay, so imagine what you're doing is you're allowing this reaction to occur. It's occurring right over, the gas is being produced right over water, simply sometimes for safety purposes or whatever it may be. The only issue with collecting it over water is the fact that water itself is going to have a pressure. Well, that's not really an issue because based on Dalton's law of partial pressures, I know that the total pressure equals the partial pressure of the hydrogen gas plus the partial pressure of water. Well, I know the total pressure in this case is 752, and I know that the partial pressure of water is 25. And so that tells me that the partial pressure of hydrogen gas is just going to be 727 millimeters of mercury. So that's the only new concept in this entire lesson, is the idea that the two partial pressures add up to give you a total pressure. Now, it's asking me how many moles of hydrogen gas were collected. Well, I have the partial pressure of hydrogen gas, or just the pressure of hydrogen gas. I have the volume. I have the temperature. I can use my ideal gas law. But in order to use my ideal gas law, I need to get into millimeters. I need to get out of millimeters of mercury and into atmosphere. So I'm going to put millimeters of mercury on bottom, atmospheres up top. 1 atmosphere is 760 millimeters of mercury. So I know that my partial pressure of hydrogen gas is 0.95658 atmospheres. Now I can plug that in to my PV equals nRT, my ideal gas law. My pressure is 0.9568. I know my volume is 0.355. That equals, well, I'm solving for my number of moles, times my R, times my temperature. Remember, temperature has to be in Kelvin, so I'm going to add 26 degrees Celsius plus 273, and that gives me 299. So when I solve for my number of moles, I get 0.0138 moles.